Ready? Okay, so working power, guys, and I'm going to be drawing all over the screen. Hopefully, I'm going to start off with a question for you. So I'll give you the 3-minute timer. There you go. It's hopefully running now. So pen, paper, and calculator. Let's see how organised you are. And I will let this 3 minutes run. Obviously, if you're watching the video, you can scoot forward once you've got the answer. But could you put your hands up for me, please, if you're in the live audience, once you've got an answer for me? And if you've got any questions, like where to start, put them in the comments as well. Okay, so hopefully I'll just sort of, without interrupting too much, I hope, deal with some of the things that catch people out here. So first things first, why can't I draw? There we go. Make sure you change minutes into seconds. Obviously this will give you your square meterage in here. How many joules? Well, a 1 watt is 1 joule per second. Okay, so hopefully if you're a little bit stuck, that might give you a little nudge. Right, remember, leave the chat empty, please, guys. Hi, Aaron. I'm hoping you're doing this question that's currently on the presentation. Oh, okay. Don't worry about the Isaac physics thing at the moment, guys. I'll explain more about that. Oh, there we go, later. I'll explain more about Isaac physics at the end of this, at the end of the presentation, just because we can focus on one thing at a time there. Okay, so what I'm going to do with this question, guys, is I already gave you some hints as we were going. I'm going to go through the working. So wherever you got to, it might give you an indication of where you need to think about improving skill sets, etc., because this will be important as we sort of want to improve your potential predicted grade. Okay, so the first thing I gave you a hint on this here is you have to work out the square meters. I don't quite know why there's a little bracket there, ignore that, it's a mistake. And you should have got 8,400 square meters. Now, if there's 8,400 square meters and it's 1,000 watts per square meter, that means we've got 8.4 million watts per second on the rugby pitch. So there we're converting watts into joules per second. So don't worry if I'm losing you a bit here. This is just a sort of putting it in perspective about the scale of what we're going to be working through. I did say you had to work out how many seconds it occurred. It's a common mistake for people. that they'll use 80 minutes instead of 4,800 seconds. And then all you've got to do, guys, is times these two together, and you'll get this lovely huge number down the bottom. And this is this is basic to GCSE level. We'd expect you to put some sort of answer together for this. Maybe not get all the parts, but some of them. And you'd be looking at 40,320,000,000 joules over the length of a rugby match. Now, what I'm really interested in this stage, and it doesn't really matter which A level you might be wanting to go to, or even any sort of applied science, if you're going to college, etc., is being able to turn this into using a prefix. Okay, and just to remind you, just in case you've forgotten, this is a prefix. So this would be gigajoules. And just to put that into some sort of context for you, a nuclear power plant might produce somewhere in the region of 1 to 2 gigajoules, depending on the size of it. So the sun's a pretty powerful little furnace. Obviously, we don't collect all of that energy, but all that energy does hit the grass on a nice, bright, sunny day. So that was a good little start to get us going. I won't throw too many of those at you, but the idea is just to sort of link in why you're learning this. Okay, so one of the things I like to remind people at this stage is we're going to talk a lot about energy stores. So I would suggest you get your pen and paper and you write energy stores, put a circle around it, and we'll put down some of the key ones. So I'll start us off. So I know I'm going to be doing a lot of the talking here. Chemical, kinetic energy. We'll do gravitational potential energy. Now I'm writing these on the outside for a reason, because in a second we're going to add in the equations for these. Other energy stores. Let's go for nuclear. We were talking about the sun 2 seconds ago. We've got sound. We can measure the energy of light. What is other ones? We've got elastic. I always feel like I'm going to forget the important one at this stage. We'll leave it for the moment, because the important thing here is just to give you a quick overview. And the kinetic energy equation and the gravitational potential energy equation, these are two non-negotiables. You're going to need them for Isaac's physics later anyway when I talk about it. So I'm hoping that you have written these down without me needing to prompt you. You should be able to recall them. But if you have forgotten, don't panic. So I'll do it properly. Kinetic energy equals half mv squared. And gravitational potential energy equals the mass times the gravity times the height. And just to remind you, for gravity, we use -10. Okay, don't use 9.8 or 9.81. Isaac Physics might use 9.8, but they will specify which one they're using for you. Okay, so that's working power. Some of our key terms, we're going to add to that as we go. Okay, so the whole thing you need to take away from this lesson is you've got to be able to describe energy transfers. These are really common in 6 markers. So whatever happens, if we do a full exam again, or you're doing a mock or an end of year exam, you want to be able to confidently use the right key terms when it comes to energy transfers. I'm going to introduce you some work and power equations. You need them today, you're going to need them in any exam that come up. And we might go on to predicting some results. We'll see where we get to, and I'll keep an eye on the time. I don't want to make this too long. Okay, so just a quick energy recap. One of the fundamental misconceptions with energy is that they all have the same principal unit. A joule is a joule. So if I have 1 joule of kinetic energy, I can transfer that into 1 joule of chemical energy. I can transfer that into 1 joule of nuclear energy. It doesn't matter. A joule is a joule. Oops, sorry, I bounced around the screen. One of the massive misconceptions is that they'll throw a question at you that might be a 3 or 4 marker, and you do some work to establish the gravitational potential energy of an object. So I'll put like a bowling ball up on top of a ladder and it falls off. The handy thing about that is that if it falls off, it's going to start moving, which means the energy is going to be turning into changing or transferring. I'm going to keep using that word. Transferring. Always transferring of energy. Always transferring. And we're going to transfer gravitational potential energy into kinetic energy. Then eventually the kinetic energy is it's going to be transferred into all sorts as it hits the ground. I've just realized one of the ones I forgot earlier, if you want to add it in, is thermal energy. Because that bowling ball, when it hits the ground, is going to transfer energy into sound, into quite a lot of thermal energy, temporarily some elastic energy, because it's going to bounce up a little bit, but essentially, and then some of it, as it bounces back up, will turn back into gravitational potential energy. We're just moving energy around. We don't lose it, we don't destroy it, we can't create or destroy it. Hopefully you've heard that term before. Okay, so if you're watching this on video later, these are some of the examples from exams that we've had in the past. Not specific, I've changed them slightly to make them a little bit more classroom friendly. But you should be looking at these kind of questions and considering some of the options you have to take place. So a really basic one on the left-hand side here is name 2 ways of lighting a room. And the obvious one is using a torch. Okay, using a torch, but there's quite a lot of energy transfers going on in a torch. You might consider using a candle, and again, lighting a match, placing it to the candle, and the candle then producing light and heat. There's lots of energy transfers always going on. This wasn't exactly the question, but it's pretty close to. It was about a boy cycling up a hill, and it was for 6 marks, and the average score was around 3, which means people were running out of steam. Well, excuse the pun. They were using some of the key terms they knew, but had run out. So it's really important that you understand this topic as a whole, and you're able to bring on, because it's a cracker for 6-mark questions. It's where they usually sit. A flow map, if you've not come across a flow map, and I apologize if you know exactly what a flow map is, but bear with me, some people don't. So flow map is when you might have, let's say, chemical in here, and then it's going to transfer into kinetic energy. Oh, sorry. That's going to transfer into GPE. And all that flow map does is lay out. Now, I don't care which walk of life you go on to next. The ability to use a flow map is an essential life skill. I know it sounds a bit nerdy saying that as a physicist, but I can take the criticism. The idea being that a flow map can be used for anything with a process, and physicists are usually pretty good at it. You'll see lots of flow maps in any engineering walk of life. Biology, big one in biology, because certain things can't happen without other things happening in specific orders, especially when you're looking at DNA specifically. Now, like I said, I'm not going to go into answering these questions live. But if you do have any questions about them later, please get in contact or send me what you think the answer is, and I'll go through with you. Okay, so one of the big things here is a misconception with terminology. And often we'll see this in a question: work out how much work is done by the student. And all work done means is how much energy was transferred. So if I have 100 joules of energy in my battery, and it'd be chemical energy, and I transfer it into the light, then I have done 100 joules of work. Okay, so it's just a term that describes how much energy is transferred. It's a fairly common misconception. Okay, so there's a question mark. Have I done something wrong earlier in the lesson? Let me just click back through. Kinetic energy, half mass times velocity squared. Absolutely. Yeah, no, that's right. I do apologize. It is a bit messy. Sorry, the question came up in the comments. I'm trying to do this on my scribble pad, and I am not very good at it. There we go. So half the mass times velocity squared, just to clarify, in case there's any confusion there. So back to where we were. Okay, so work done, which is just energy transferred. We can look at, in this instance here, the amount of force you apply. So this topic is talking about forces and how far you move something. Now, if I don't move something anywhere, so I apply a force and I don't move it anywhere, it'd be times 0. Anything times 0 will be 0. So if I don't move it, no work is done. So that's probably not particularly useful keep that. Let's get rid of that. And again, like I said, these are interchangeable. Okay, work done is just a measurement of energy transfer. So the energy is just the force times the distance. Please make sure you write both of these down because you're going to be using them. For those of you who do triangles, I can't do the triangle off the top of my head because I always get triangles wrong because we don't use them for the more complicated equations. Where did I see the triangle? Oh, I saw the triangle in the textbook that you guys had in the classrooms. If you don't have an online link to that, if you Google this equation, you'll find the triangle there and then. Okay, so this was a GCSE question, except I changed it to Gertrude. And it's all about pushing her fridge as hard as she can, and it's a fairly common problem. How efficient is Gertrude being? Now, when they asked this question here, how efficient, everybody forgot about this part of the question. But it doesn't move. Okay, this is the key thing. It's in red. Doesn't move. Remember I said if anything is times 0, the amount of energy transferred is 0. So she's applying all this force, and we got all sorts of answers. We got 3% and 10% and 20%. And people were just making up random numbers. The answer, of course, 0%. Okay, so thank you for those who just posted in the comments. You're spot on. If you're not moving something, you're not being efficient, which makes sense. Okay, so I just want to quickly go over efficiency because we're going to use it quite often. I'm going to talk about some efficient objects in real life-ish. So efficiency is, and we can summarize this equation here. So you can just, efficiency equals useful energy divided by the total energy. Oh, I suppose I should probably write this out. Efficiency equals useful divided by total energy. Okay, so here's a question for you. It's a work example, fairly typical. A phone is transferred 100 joules of energy, but only uses 80 joules before going flat. Now, it's pretty obvious there's 20 joules missing somewhere. It doesn't just disappear. I'll deal with that first. It's nothing to do with the question, but the 20 joules will have gone off as probably heat. And you'll know this because if you use your phone lots and you're charging it lots, etc., you'll know that your phone gets very, very warm as that energy is transferring. That's just a consequence of transferring energy. Almost always there is some heat loss. Prove a point to you if you're at home today and you're making, oh, actually, you should probably check with your parents before doing this. If you boil the kettle, there you go, I gave you a safety advice on boiling a kettle. If you put your hand on the cable that's plugged into the wall after you boil the kettle and it's safe to do so, you'll probably find that the cable is warm, only because kettles transfer a huge amount of energy really, really quickly. Isn't thermal the most wasted store? Yeah, that's one of the questions that came through in the comments. Yeah, absolutely. It's not the only wasted store, but probably the most wasted store. So in answer to my question earlier, a phone is transferred 100 joules of energy. So we just take out, I think it's going to come off if I press it. There you go. Efficiency device, we're going to take out 80. We're going to divide it by 100 because we were given those two numbers, 80 and 100. And if we want to get it as a percentage, we times it by 100 again. So this would have just come out as 0.8, which would have been a perfectly suitable answer. Okay. But if you want it as a percentage, you just times by 100 and 80%. Now, a little trick here, guys. If you're ever dealing with efficiency questions, it doesn't matter what walk of life. If you get over 100%, you've probably just got these two numbers the wrong way around. Okay, so just flick them around. So it should be under 100%, unless you're about to become very wealthy from creating something that's in perpetual motion. 80% efficiency for a phone would be a pretty decent phone. Some of you will know that for some of the older iPhones were not that good in terms of charging and discharging really, really quickly. I don't think you guys will be old enough to remember the iPhone 3S, which was a really big popular one when iPhone really took off. And that was horrendous. If you spoke for about 25 minutes straight, your phone was hot enough that it was difficult to handle. But obviously, they've improved technology dramatically since. So, without further ado, I'm going to talk about our falling tennis ball. And now, I did allude to this early in the lesson. I talked about a bowling ball being up on a... You're going to go and boil the kettle now. Thank you, Toby. That's very practical of you. We did talk about a bowling ball falling off. This one is a tennis ball. And you guys, if I asked you to describe a tennis ball falling off, you'd be able to do it. You'd be able to tell me all the key parts. Don't worry about the questions for the moment. I'm just going to bounce it along. Bounce it along. And you guys would probably, or without me prompting you much, would realize that the tennis ball doesn't bounce up to its original height. Okay, this is all about energy transfer. So to start off with, we've got lots of GPE up here, gravitational potential energy, but tennis ball's not moving vertically. As it falls off, it's going to get faster and faster and faster, and the kinetic energy is going to go up. And this is just what we were talking about earlier. And as we go back up here, it'll all be just transferred back into gravitational potential energy. This difference here between the two heights is going to equal an amount of energy. Now, it's almost certainly going to be mostly thermal. And those of you who play tennis will know if you hit a tennis ball around a lot, you'll notice the tennis ball actually gets warmer. Squash balls, for example, you can't play a game of squash without heating the ball up first. I know most of you probably don't play squash. Take it from me that squash balls get quite warm. And I never get this right. Someone will correct me for sure. In Wimbledon, when they changed the tennis balls, I think it's every 8 games, but I guarantee you, sorry, I'm shaking the table. I've got that wrong. They changed the tennis balls because they wear out, because the heat inside the tennis balls, and they're hitting the tennis ball at 200 kilometers an hour. So it's not a massive surprise that it's getting squished and those energy transfers are taking place. The energy is not lost, it's just transferred to the environment. So the tennis ball doesn't get red hot, but it does get quite warm while it's getting squished backwards and forwards. Okay, so that's why doesn't it bounce? Well, we just talked our way through that. Okay, so 2 questions for you here, guys. Those of you in the live lesson, if you're watching, could you please have a go at these? Use the same equation. Put your hand up for me when you're done. Ask questions if you need to. Those of you watching it on a video, could you please pause the video and I'll put the answers up shortly. In answer to your question, Toby, the tennis ball gets hot not because GPE is converted into thermal energy. It's usually the tension or elastic energy is converted into thermal energy because you're stretching and pulling the particles apart and pushing them back together. So just remember, can you put your hands up when you got an answer, please, guys? We'll do the first one, if you like. So if you've done the first one, could you put your hand up for me? Anybody stuck? If you want some help, put something in the comment section for me. Okay, a few more hands popping up here. So I'm just looking for the first one at this stage. That way, if you're getting stuck, you can at least see if you got the right answer. Remember, it shouldn't be above 100%. Okay, I think we've got a majority of people there. If you put your hands down for me, I'll put the answer up for the first one. Okay, so it should have been 33%. And the way I would expect to see the working out would be literally to write the equation useful divided by total and then stack it underneath. So useful was 500 and total was 1,500. Now, they are in kilojoules, but it doesn't matter because they're both in kilojoules. And then we could have an answer of, well, it'd actually be 0.33. But we times it by 100 to get our percentage of 33%. Now, there is a contentious issue with the second one. It is important that you recognize what the total useful energy is. Put your hand up when you had a go at the second one, please. Okay, so hopefully, well, I think we've got most of you there, so you can put hands down. I'll put the answer up. Now, obviously, I'm assuming here that you have got 100 joules of kinetic energy and 500 joules of thermal energy are both useful. So it'd be 100, I'm skipping a step, sorry, so I can fit this in. I'd normally write the equation out above. 500 over 800. So if you only did 500 over 800, you also need to include the fact that that kinetic energy is useful. Okay, so that's a basic introduction to understanding efficiency and work and power. So go into a little bit more detail on power now. So power is all about the rate energy is being transferred. So right at the start of the lesson, we talked about the sun applying energy to the grass, and that total time of rugby game was 40 gigajoules or something around that. What we're interested in when we're talking about power is an instantaneous snapshot. How much is being transferred at an exact point of time. Now, this is really important for the chemists amongst you. Obviously, we treat it in physics as a fundamental, but when you're looking at certain energy transfers in chemistry, you need to make sure you don't exceed certain energy transfers. Case in point, people are making nitroglycerin. If you make it too fast, it's what we call a runaway reaction, and it will go kaboom. And many people lost their lives doing so. So when nitroglycerin is made, it's made in an ice bath, and it's the rate of reaction, good chemistry link here, the rate of reaction is slowed down by using the ice bath and increasing the surface area with the ice, cooling the temperature so you don't get a runaway reaction. So power is the rate of transfer. So we literally just take the amount of work done and we divide it by the time. And again, I alluded to this right at the lesson, start of the lesson, 1 watt equals 1 joule per second. Sometimes that's written as 1 JS1 or 1 joule per second. They all mean the same thing. But you should be fairly familiar with some of these terms. They would have come out at the start of year 10 for you, but this is just a nice way of reminding you as well as you need it for Isaac. Okay, as long as you've got that written down, that's obviously a big one. So if you get asked a question about what the power, or you have a power and amount of time, it's just a rearrangement of this. So you might have work done equals power times time. Okay, so that's a fairly common one. So if you've got a microwave, and if you have a look on the front of your microwave, it might say 900 watts, and you're putting your 900 watt microwave oven on for 20 seconds. 900 times 20 seconds is 18,000. So you transfer 18,000 joules of energy into your food in that 20 seconds. So there is a practical element to this in everyday life. If you put too much energy into your food, it burns. It's no different in a microwave than it is on the stove. Okay, let's move that on then. Okay, I'm not going to get you to do this, those of you joining live. This is something I do in classroom, talking about actual everyday people's lives, transferring energy. But I'm going to move on to something a little bit more interesting. Now, I'm going to see for the first time if this works live. So bear with. I need to get back to my clicker. Now, these are YouTube videos, and they tend to be a little bit loud, which is great in the classroom. Now, I'm not sure if you can share it. Hold on. Right, ads. Here we go. How do I get back to you guys? share. Hang on 2 seconds. I'll pause. Right. I'm assuming you can only see my PowerPoint at the moment. It's where an embedded would be really handy. How do I actually see? Oh, I don't know if I'm going to be able to do that. Andy. Sorry guys, bear with. I'm trying to find if I can play this. I'm presenting. Now I'm going to keep presenting. Change layout, full screen, captions. Change layout. No, I won't change layout. Right, sorry guys, I don't think I can do that. Change the presentation screen without stopping the presentation. So what I was going to show you was a picture of a video of an F-16 fighter jet spooling up. I'll put the links in the classroom area later, and a similar on a turbofan on an aircraft. And the idea was looking at how much airflow and how much fuel is being transferred, the energy transferred from the chemical energy store into the kinetic energy store and thermal store of the engines. But that doesn't seem to want to play ball. So you're absolutely right, Toby, but don't worry about that too much at the moment. It's more about the energy transfers. Okay, so this is sort of my last bit for you. So it's all well and good me talking about F-16 fighters and passenger aircraft, but I'm pretty sure none of you own that. So I wanted to bring it back into a little bit of reality about things that you would have in your everyday life. And hairdryers are a classic example. Same principle as a fighter jet engine. You have an energy transfer taking place. You're trying to convert that into kinetic energy of the air and adding heat to the air. So you get expansion, and therefore the gas travels faster, pushes the fighter jet fast, quicker, and obviously with a hairdryer, the idea is to dry your hair faster. But of course, the hairdryers aren't incredibly efficient. And those of you who used a hairdryer before, as you can probably tell, I don't use one that often, is that they tend to get hot around the outside of the case. So one of the things that I would ask you to do in class would be to think about changing the design. Now, this is not just applicable to physicists. This could be someone who wants to go into product design, someone who's thinking about sales or marketing, because clearly you can't make a hairdryer that's got a huge amount of insulation wrapped around the outside. It would solve the problem, but no one would buy one. So this is about using physics to solve everyday problems. Now, I'm just going to stop the presentation there. So this is something you could potentially be set as a little bit of homework, depending on which year 11 class you're in. And I will leave that up to your teacher to decide. So bear with me while I stop the recording.